Hey Peyton, how are you doing? Good.
Good, how are you?
I'm good. Good to talk to you again.
Did you get,
I did.
yeah,
We're
yeah.
looking at it.
Um,
So how's Trig going?
okay. It's going, it's going all right. I'm kind of having a little bit of, troubles on like, the latest, like, trig functions and stuff.
Okay. Well, let's go through these.
Okay.
What's the first step here?
To get, secant of, theta by itself, right?
Okay. So what do I need to do?
Subtract, or add the 2 to both sides.
All right. Now, if you are like me, you prefer to think in primary trig functions, which are sine, cosine, and tangent.
Yeah.
And when they give you these secondary trig functions, they become difficult. And so what I always do is switch them to primary trig functions.
Okay.
What's the reciprocal of secant?
Isn't it 1 over cosine?
So that's what I'm going to write. Now do the algebra. What's cosine of theta got to be equal to?
Um, um, like one half.
There you go. Now that's an easy problem, right?
Yeah.
Compared to what we're looking at in the beginning. Now, well, first of all, let me look at your problem again. Do they put any domain on these? Yeah, 0 to 2 pi.
Yeah.
Okay, so if theta has to be between 0 and 2 pi, where does that happen? Where theta, the cosine of theta equals 1/2.
Um, well, don't we list, well, that's like that, that's like around the entire unit, like, it's from, like, yeah,
There's going to be two quadrants
yeah.
where the cosine of that angle is equal to 1/2. Well, let's start with the easy one. What about the first quadrant?
Yeah, it would be in the first and second quadrant, right?
No, let's take the first quadrant first.
Okay.
What angle,
Well,
what angle is the cosine of that angle equal to 1/2?
uh, pi over 6.
It's pi over 3, 60 degrees.
Oh, yeah, no, yeah, I got mixed up with sine and
In other
cosine.
words, well, here's your two triangles. Never forget these two triangles. These two triangles give you all of your first quadrant answers.
Yeah.
The 30-60 and the 45-45. As long
Yeah.
as you remember these two triangles, you will never miss any first quadrant angle.
Yeah.
In other words, for the cosine to be 1/2, it has to be 60 degrees because it's adjacent over hypotenuse.
Yeah.
So theta would have to be 60 degrees, or you're using radians more.
Pi over 3.
Okay.
Yeah,
Now,
we use radians
where
right now.
else, based on this, is cosine positive? Which quadrant?
Um, wouldn't it be,
What's the ASTC stand for?
um, wouldn't it, isn't that like all, isn't the S for sine and then T for tangent
Okay.
and C for cosine?
Okay, so where is the cosine positive? Which quadrants?
Oh, it's going to be like the fourth quadrant at,
Okay.
yeah,
In other words, we've got the first one.
yeah.
What is the equivalent fourth quadrant angle for pi over 3?
Wouldn't it be 5 pi over 3?
There you go. Those are your two answers to this problem.
Yeah.
In other words, we turned it from a secant problem into a cosine problem. And then once it was a cosine problem, it was pretty easy.
Yeah.
but we still had to know where cosine of theta is equal to 1/2 in the first quadrant. And then we have to figure out that equivalent angle in whichever other quadrant where it's positive. And there's always going to be two quadrants where the trig function is positive. So whenever they restrict your domain to 0 to 2 pi, well then you're almost always going to have two answers.
Yeah.
Sometimes 4 if it's plus or minus 2. But let's look at the next problem. Any ideas what we should do here? Again, x is going to be between 0 and 2 pi.
Yeah. Well, I mean, what we did in class, we like factored it, so we could like subtract the 1 and then factor everything.
That's the correct way to do it. In other words, it's really what we're looking at is a quadratic. In fact, I call it a quadratic in disguise. It's not a quadratic in x, it's a quadratic in cosine x.
Yeah.
I can't factor it yet. In other words, just like quadratics, I need the other side to be 0. So this needs to be my first step. Now I can treat it like a quadratic.
Yeah.
Well, I know it's got to be 2 cosine x and cosine x for starters. What's the rest of it?
Wouldn't it be plus 1 minus 1?
Yep. In other words, we know that's correct because if I check my inside term, I got that. I check my outside term, I get that. Add those together, you get that, and that is our middle term.
Yeah.
In other words, you always want to check your middle term. That's where people make the mistakes, is the middle term. And now, you don't need to check the 2 cosine squared x or the minus 1, but you need to check the middle term.
Okay.
Correct? Okay, now what?
Well, now you can solve for x for each of them.
Okay.
So like, so set 2 cosine x plus 1 equal to 0.
Okay, which gives you this.
Yeah.
And then set cosine x minus 1 equal to 0, which gives you that.
Yeah.
Now let's take the first condition. Which angles is that true in the unit circle?
Isn't it like the 2 pi over 3 for the first, for the first one?
Yeah, in other words, the cosine is negative in the second and the third.
Okay.
Positive in the first and the fourth. So I need to come up with the second quadrant and the third quadrant. And you're correct. The second quadrant is 2 pi over 3, which is the equivalent of pi over 3 in the first quadrant.
Yeah.
Now what's the third quadrant angle?
Wouldn't it be 4 pi over 3?
Got it. So there's two solutions. And now we have also, where is cosine x equal to 1?
Isn't that just 0? Or yeah, isn't that just at 0?
And it's the only place.
Yeah.
If we draw our cosine curve, some of these quadrangles only have one answer. Okay? Notice there's only one place where cosine is equal to 1, and that's at the beginning and the end. But notice this domain's got a less than 2 pi, not a less than or equal to 2 pi.
Yeah.
So we can come up with 0 as an answer, but not 2 pi.
Yeah.
So 0 is the only place in the unit circle where cosine of 0 equals 1.
Okay.
Okay? And that's true also of sine. Notice that there's only one place where cosine's equal to -1, right there.
Oh, yeah.
Also true of sine. Notice there's two places where cosine's equal to 0. So it's only when they're equal to 1 or -1 that you only end up with one solution in your answer. Now, they probably have a problem like this, but what if one of my solutions, let's make that a 2, like that, okay?
Okay.
Let's just say that that was our quadratic. We'll make that a -2, and we'll make that a -3. Then it would factor this way.
Yeah.
Okay. Now we would still have cosine of x equal -1/2 for this part. But then we would have cosine of x equal 2 for this part. Well, where does that happen?
Wouldn't that be at like two pi?
At never. That's where.
Oh, no. Okay.
Cosine
Okay, yeah.
x cannot be greater than 1 or less than -1.
Okay.
In other words, that domain is restricted for both sine and cosine. Doesn't matter whether I'm drawing the sine curve or the cosine curve. The sine curve's never greater than 1, never less than -1.
Okay.
If I draw the cosine curve, same thing. So if somebody tells you that the sine of an angle is equal to 1.1, no, it is not. That's impossible.
Okay.
Okay? And they will give you problems sometimes that when you go to solve the quadratic, you get that. Okay? So
Yeah.
you got to watch out for it, because you will see problems where they will tell you the sine of an angle equals an impossible number.
Yeah.
All right, what's the first thing I want to do here?
Divide the 4 out.
Next thing.
And then you square root both sides, or yeah, square root both sides.
So what's sine alpha equal to?
Wouldn't that be 1/2?
Plus or minus?
Oh yeah, plus or minus, yeah.
Biggest mistake that my students make is that one right there.
Yeah.
When they take the square root of both sides of an equation in order to solve it, always begin your answer with the words plus or minus. No exceptions.
Yeah.
No exceptions. Okay? It's whenever you're solving an equation by taking the square root. That's
Okay.
where everybody makes the mistake. They always leave off the plus or minus. And it's going to matter big time here, right? Because
Yeah.
the plus would give us 2 quadrants, and the minus is going to give us 2 other quadrants. So the plus or minus is actually going to give us 4 answers. What's the first one? Where's the sine equal to plus 1/2?
Isn't that going to be pi over 6?
Where else? That's first quadrant.
5 pi over 6?
That's second quadrant. Now how about where is it equal to minus 1/2?
7 pi over 6 and 11 pi over 6.
Oh, I like the way you're converting to radians. I can tell you're thinking in radians, not degrees.
Yeah.
It takes a lot of people a lot of time to do that. Most students will convert to degrees and then convert back to radians if they have to be in radians. But not very many students that learn to think in radians, but I can tell you're doing it.
Yeah.
Those are your 4 answers. Notice that if we forgot the plus or minus, we would only have those 2 answers.
Yeah.
So you would definitely lose points if you forgot the plus or minus.
Yeah. I'll have to remember that.
You would just lose a few points. Solve each, let me blow this up so I can see the instructions. All possible solutions. Okay. That's different. Don't really like that extra instructions, but
Yeah.
I'll live with it. Sine of 2 theta equals cosine of theta. I presume at the same time that they are saying you can't use your calculator.
No, yeah.
Because if I could, this would be y sub 1, that would be y sub 2, and I would just look for where they crossed.
Yeah.
That's the solution. But they don't let us do it that way.
No.
So, when you have a trig equation that has two different kinds of trig functions,
Yeah.
your goal is to change it so that there's only one kind of trig function.
Yeah.
So, what's an identity for sine of 2 theta that has some cosines as part of it?
Couldn't we use like the
What's the identity for the double angle formula for sine?
wouldn't it be sine 2 sine 2 theta equals 2 sine theta cosine theta?
That's what sine 2 theta equals, right there.
Yeah.
Okay, now you might think that at this point I could divide both sides by cosine theta.
Yeah.
But here's the problem with doing that, is if 0 is one of the answers, you lose it.
Oh.
Because you cannot divide by 0. And it's
No,
entirely possible that cosine of theta could be 0, right?
Yeah.
I don't know that it's not 0, so therefore I cannot divide by it.
Okay.
Okay, the way to solve this problem is to subtract the cosine theta that's on the right from the left,
Okay.
leaving behind a 0. Okay?
Yeah.
Now I can factor out a cosine theta.
Yeah.
And leaving behind a 2 sine theta minus 1.
Yeah.
Now I got two quantities multiplied together equal to 0. Well, one of them has to be 0. So either cosine theta has to be 0, or let's just say sine theta has to be 1/2.
Okay.
Without the 2. I meant to do that step all at once. Okay? So either of those can be true, or both can be true. Well, where's cosine theta equal to 0? And they want all solutions.
Well, that's that
Here's what cosine theta looks like. So we want that solution, we want that solution, we want that solution, we want that solution. All of them out to infinity. Well, where's the first one? Where's that?
Wouldn't that be at pi over 2?
Okay, so theta, if I draw an arrow down here, theta equals pi over 2, or what?
Or
It's the second 0 there.
3 pi over 2.
All right. Now, the way to do these infinite series problems, and that's what this is because they did not restrict it to the unit circle,
Yeah.
is to add multiples of 2 pi to both answers.
Yeah, that's...
Do that
Yeah,
is like that, either using an N or a K. What does your school use?
We use K's.
What that means is that K is going to count up by integers, all the way to positive infinity and all the way to negative infinity.
Okay.
Notice that when K is 0, my answer is pi over 2. When K is 1, my answer is 5 pi over 2, which is that spot right there.
Yeah.
Now, going to the second answer, 3 pi over 2. I also want to add multiples of 2 pi to that. Okay?
Yeah.
And that is this spot right there, and again, this spot right there. So
Okay.
every multiple of 2 pi, I'm going to have that same 0. Now, you might think that I could combine these. Maybe I can. Let's see. If I said theta was pi over 2 plus k pi, does that include all my solutions? Well, it gets
No.
pi over 2, and then when k is 1, I got 3 pi over 2. When k is 2, I've got 5 pi over 2, my next solution. This actually handles both of them.
Okay.
And never write in 2 equations what can be written in 1. Most of these answers, you got to use 2 equations to write it, the infinite series. But always check and see if 1 equation won't do it. In other words, when I used 2 equations, I was doing multiples of 2 pi. But I thought, well, this is just a multiple of pi above that. So let's try pi over 2 plus k pi and see if I get all my solutions. And I believe that I do. In other words, I get the blues and I get the reds with this answer right there.
Yeah.
That gives you every one of them on both sides of the y-axis.
Yeah.
Gives you this one, gives you this one, just those are negative k's. -1, -2, things like that.
Okay.
Okay? So when you have these problems that do not restrict the domain and you have to give your answer as an infinite series, the best way to do it is to list your first 4 or 5 answers and then see if you can put them in an infinite series. And by that, here's what I should have done. If I wanted to list my first, well, pi over 2 is certainly one. 3 pi over 2 is the next one. This one here is 5 pi over 2. This one here is 7 pi over 2. Well, now I can see there's a series going on there. And what is the series? Well, it's the first term, pi over 2, plus what do I have to add to it to get to that? I got to add pi.
Yeah.
And then, if I make k 2, then I get 5 pi over 2. And if I make k 3, I get 7 pi over 2. So this series defines every term in my series and does not skip any. And that's the important part.
Yeah.
Like I said, you won't always get one that can be defined with a single equation. A lot of times with these cosine and sine problems, you get series that look like 5 and 7, and then they go back and 11 and 13, and you can't put that in a series with one equation. You need 2 equations.
Yeah.
So be aware of that. This one we could do with 1 equation. I'm betting that they've got another one here that takes 2 equations to do.
Okay.
I'm booked up pretty solid tonight, Peyton, so I'm going to have to run at 6. Let's see how far we can get this in this next problem here.
Okay.
I can certainly get it set up for you. Again, we're looking at something that looks like a quadratic, right?
Yeah, so we would add the 1.
In other words, solve it just like you would solve a quadratic, a polynomial, an algebra expression.
Yeah.
So that's my first step. Now factor it.
Wouldn't it be 2 sine of x? That
has to be true right there.
Would it be +1 -1?
What do both of my signs have to be in order to produce a +1?
Oh wait, oh no, yeah, they have to be
the same.
Yeah.
They either have to both be minus or they have to
they'll both be minus since it's a -3 sign.
Because the middle term is minus. Now the factors of 1, we don't really have any choices, 1 and 1. And if that doesn't work, we're out of luck. But if we check, that's -1 sine x, that's -2 sine x. Add those together, we get -3 sine x. That's correct. So it does factor like that.
Yeah.
Now, take the next step, which is setting each one equal to 0. So you get sine x equals 1/2 from the first one. And the other one, you get sine x equals 1. And again, this one only happens at pi over 2.
Yeah.
And multiples of pi over 2. Whereas this one happens at pi over 6, 5 pi over 6, and multiples of that. So the next one is going to be 13 pi over 6, and if I add 17 pi over 6. In other words, the way you kind of want to do these is add 2 pi to the first term and add 2 pi to the second term.
Okay.
Okay. Now if I were to lay out my answers, I got pi over 6, I got 5 pi over 6, I got, there's a pi over 2 in there. Pi over 2, if I put them in order. And I got 5 pi over 6. And then I got 2 pi. No, I don't have 2 pi. The next one in order would be 13 pi over 6.
Yeah.
And then I would have 5 pi over 2, and then 17 pi over 6. I may have those out of order.
Yeah.
No, that's the right order. But
okay.
Notice, now that one's not so easy to put into an arithmetic series, an infinite series. And in fact, you can't do it with a single equation.
Yeah.
So I go back, and in fact, this one's going to take 3 equations. If I do this one, my answer is x equals pi over 6 plus k 2 pi. That gives me that term and all future terms.
Yeah.
Another answer is x equals 5 pi over 6 plus multiples of 2 pi.
Yeah.
That gives me that answer and all future ones. And finally, there's a third equation. And that's for this one right there. In other words, x is also equal to pi over 2 and all multiples of 2 pi.
Okay.
So there are your 3 answers to that problem. And that's the most efficient way to do it. There's no way I can do it with a single or even 2 equations.
Yeah.
And that's the best way to do it, is to lay out the series like I've done.
Yeah.
See, the series is 1, 5, 13, 17.
Yeah.
You can't do that in a single equation. You got to do that in 2 equations.
Yeah.
Those 2 right there will give you that series.
Okay.
Then this series requires the third one.
Okay.
All right. Peyton, I got to run. I will talk to you next time.
All right. Thank you.
All
Bye.
Right. Bye-bye.